Okay, so we'll have a normal distribution problem. We'll be given a population mean and a population standard deviation. We'll also be given that you have a normal distribution in this kind of problem. And the question will be something like, find the probability that x is less than 20. Of course, it could be between 2 points or greater than some value. And if you're not sure of the difference of those, you may want to go get some more practice on those. But so we have that information. Draw a bell curve. At least this is how I think you should proceed. If you're in the classroom section, you'll need to show all of this. If you're in the online section, I still recommend that you draw this. This is, I think, is the, especially on a multiple choice, the tendency maybe not to draw them, but then to forget whether you should subtract from 0.5 or whatever you need to do once you get your z's and so on. So I just have a normal curve here with the axis labeled. In this case it's x. Remember, we get to sampling distributions, that's going to be x bar. And also when we do hypothesis testing, it'll be either x bar or p hat, and then other statistics as we go on. But for now it's just x. And I have the mean and the standard deviation, and I've shaded in the area that we're asking about. Is what proportion of values is less than 20. If we get this on the test, it's not going to give you these symbols. It's going to say that the population mean is 24.3, the population standard deviation is 3.72. You'll need to translate those into symbols, and it'll say find the likelihood that you get a value of whatever it is, a number of dollars, for example, less than 20 if it were a problem about dollars. So then z is just the number of standard deviations from the mean. So x minus mu over sigma, and then you get a 1.96 in this case. That is the number of standard deviations from the mean. I'm going to move fast. If you need to pause to write this down, then you should do that. So we look that up in the z table, and so we find that the area between 20 and 24.3, this area in here, that's the 3770. And since that's not the area we're looking at, but we know from here down is 0.5, we will just subtract that from 3770 from 0.5 to get our answer. So the answer that is the area in the tail over here is 0.1230. Okay, so here is another example. This time it's fine from 26 to 30. And what we're going to find here is that we can't get that directly. What we're going to have to do is get the area all the way from 24.3 to 30. And then we can get the area just out to 26. And our answer will be the difference between those two areas. So there's just our formula for a z value. We'll get for area A, that's the area that's all the way out to 30. So 30 minus 24.3 divided by the standard deviation. 1.53 standard deviations away gives you an area of 4370, just looking up the 1.53 in the z table. Same thing for this one, it's just subtract 26 minus 24.3 divided by 372. Not quite a half a standard deviation away. So that's this area right here. And so the difference, which is the answer, is 0.2598. Percentiles, which quite frankly is the one that I think students have the hardest time with. It's not that difficult, just follow through the steps here, draw the picture. We're looking for an x such that 20% of the values are below that point. And what we're going to have to do, first of all, is find this area, which of course is going to be 0.3, since from the mean down is 0.5. And then, remember, we can only go from the mean to some point. Well, that was obviously my dog, Peyton. Someone was walking by the house. Well, anyway, back to the problem here. We have 0.3, and then I'm going to go into the center of the table, the center of the z table, find a number that's close to 0.3. I believe that the closest number that you'll find is 0.2995, and so you're in the table. You've got your z table, looks like that, and you're around here on the table, and you find the number 0.2995, and then go out and read the z value out in the margin, and it's going to be 0.8, and then read your column, and it's going to be 0.4. So 0.84, I think it'll be 0.04. 0.84, this just gives you the stem, and then here's the place in the hundredths. So we're 0.84 standard deviations below the mean. In fact, you could put a minus there. That's not usually how I do it. If you just solve the formula outright, that's what you would need to do. But I prefer just to draw that and realize that that point is the mean minus 0.84 standard deviations. And just doing a little math here, you get 21.18. Okay, so now here's a slightly different problem. In this one, it would still give you a population mean and a population standard deviation. And at the sample size of 4, we still need to know that the population is bell-shaped. We don't have a sufficiently large sample for the existence of skew or outliers, extreme values. But the difference in the question now is we have a sample size, and it's going to say find the probability or the likelihood that you get a sample mean. Again, I'm not going to give you the symbols, but find the likelihood that you get a sample mean in some area, in this case greater than 26. So, crucial step, make sure this is the sampling distribution of x bar. So the standard error of that sampling distribution is equal to the population standard deviation divided by the square root of n. This is all related to the central limit theorem here. Someone's driving by now. She'll keep you apprised of the situation in the neighborhood. So anyway, once you've done that, the problem is very similar. The formula is different, but the whole process is very similar to what we just did with a normal population. It's just that now we have the distribution of x bars. Make sure you label the axis, that you know what goes on that axis. I can make that into a multiple choice too. The mean of the x bars is equal to the mean of the population. The standard error is equal to the population standard deviation divided by the square root of n, as we've done here. So from there, follow the same procedure. Now, instead of being x, it's x bar minus the mean of the x bars, the mu x bars, divided by the standard error of the x bars. 26 minus 24.3. That's giving us this area. We find that that has a z of 0.91, which just means that this point, 26, is not quite one standard deviation above the mean. It's 0.91 standard deviations above the mean. To find the probability, we'll look that 0.91 up in the z table to get a probability. Again, that's this area. And so we'll have to subtract from 0.5 to get the answer. So the answer, the area out in the tail here, is 0.1814. Okay, so now we're going to have a hypothesis test. Again, it's going to be in words. Might be something like, in a sample of size 25, find the probability that we get a sample mean, or in a sample of size 25, we get a sample mean of 16.3. It'll say we know the population standard deviation is 4.16. Since you know the population standard deviation, it's going to be a z-test. And then it'll have a question that says something of the effect, is the population mean less than 18? And looking on here, I don't think I wrote the hypotheses on here, but the hypotheses would be HO and H1 or A, whatever you want to call it, or R, always an equal sign, and for the alternative, whatever the question is and the problem is the population mean less than 18. Again, that'll be in words in the problem, but same thing. We will reject HO if the p-value is less than 0.05. That statement won't change. We'll always reject HO if the p-value is low. So I guess the only thing that could change is whether this was 0.05 or 0.01 or some other value. Frequently it will be either 0.05 or 0.01. Others are possible, but those are the most likely. So now I'm going to compute the z-test, and keep one of the things that in here I always say is that if you realize what you did in the problem before, this one is just an adjustment to that. It's still on the top the difference between the sample mean and the mean of the, but now it's the hypothesized mean here instead of some known mean already. This is the hypothesized mean of the 18, and then your standard error is still the standard deviation of the population divided by the square root of n, which was 25 in this case. So we get a z-value of minus 0.204. That means that the 16.3, the mean that we observed in the sample, is about 2 standard deviations below the hypothesized population mean. And put that all out in a picture here. So this is just a picture of what we just had. Distribution of the sample mean, the hypothesized population mean, the sample mean that we did observe, and then the p-value will be the area in the tail here. We've already computed this to be about 2.04 standard errors below the mean. Look that up in the z-table to get an area of 4793, and the p-value is the area in the tail, the 0.0207. Which is less than 0.05. We said we would reject if it was. So we do reject HO and conclude that the population mean is less than 18, that we're confident that the population mean is less than 18. It's just sort of a redrawing of the thing, just a little, intended anyway, to be a little bit simpler. So when you ask for, or when I ask for, or when a multiple choice question is asking for an interpretation of the p-value, it's always, if HO is true, remember our HO was that the population mean was equal to 18, then there is a p-value chance, that's 0.0207, the area in the tail here, that we would get a statistic as or more extreme than the one that we obtained in the direction of the research hypothesis, which was less than in this case, so that we would get 16.3 or less than or equal to 16.3 in this problem. Similar thing here, except for now, instead of saying less than, the question might say, is the mean different from 18? So some things are going to be the same. We're still going to reject HO if the p-value is less than 0.05. We're actually going to compute the t-test exactly the same. So we have minus 2.04. Again, that hasn't changed. Actually, there's two differences in here from the problem we just did. One is that we had a two-tailed test. Trying to move through this pretty quickly. This is a sample standard deviation, which means this is going to be a t-test. So let me go back a second and just say that even though the numbers were the same, this is different. It has s divided by the square root of n. So we're talking about a t-test. And so that's going to affect the p-value because the t distribution is a little flatter, more spread out. And you can think of it this way, that we've introduced another degree of uncertainty into the problem because we don't know the population standard deviation and it has to be estimated. So to get that p-value, I'm going to recommend that you use your calculator, your statistical calculator. And if you have your statistical calculator, if you don't, you should probably get it and look at this. Select Stat, arrow over to Test, arrow down to the t-test, that's the second one down. At the top of the screen, there's an input, and it's either going to say Stats or Data. Well, for this problem, since we have the statistics given to us, we'll say Stats. Then we'll enter at the top, the first thing it asks there is for the null hypothesis, so you'll put 18 there. Then you'll put in the sample mean, the sample standard deviation, the sample size. And since this says not equal to, it's a difference here, you'll select not equal to, and then just hit calculate, and it'll tell you that the p-value is 0.052. Please make sure you can use the calculator on the test, especially on the multiple choice questions. You don't want to spend a lot of time working things out when you can just do it on your calculator. This is a two-tailed test, so that 0.052 is actually a combination of the probability up here and the probability down here. So when we go to interpret our p-value, I know the two-tailed is a little trickier to say. The first part's the same. If the null hypothesis is true, the population mean is 18, then there is a p-value chance, that's the 0.052, that you would get a sample statistic this or more extreme in the direction of the null hypothesis. Well, that includes, remember the hypothesis was not equal to, so it includes this area here, but it includes an equal area on the other side. So really this area over here was probably about 0.026. So since this distance is 1.7, that's just 18.3 minus 16.3, we'll go up to 19.7, that same distance, 1.7 subtracted from 18, 1.7 added to 18. So that's how I got the 19.7. So again, now back to the statement. If the null hypothesis is true, mu equal to 18, then there's a p-value chance that we get either this, less than or equal to 16.3, or greater than 19.7. Okay, effect size is just, the numerator will be the top as the hypothesis test, sample mean minus hypothesized mean, but just S on the bottom, not SX bar. So now we'll set that up here. That comes out to be minus 0.41. Just take the absolute value of that if you want. The size of the effect is 0.41, which using Cohen standards would be a small effect. Less than 0.2 would be trivial, between 0.2 and 0.5 small, 0.5 to 0.8. Medium above 0.8 is large. I'll have that on a formula sheet for you. You don't need to really memorize that. So now for the confidence interval, make sure you know this one pretty thoroughly because there are going to be several questions in the exam bank that will test that you know the whole formula and how you got to it. So the first thing is we have to have degrees of freedom, and that's 24. Okay, if you'd already written this down, please go back and rewrite. Thought I'd fixed this already, but anyway, degrees of freedom is 24. Confidence intervals are always the statistic, in this case, x bar, plus or minus the confidence coefficient, which will be at 0 t, since we have sample standard deviations at t, times the standard error, which is s divided by the square root of n. So these you can just read right off the problem, 4.16 divided by the square root of 25. You'll need this t value, the confidence coefficient, so go to the t table. At the very top of the t table, it'll have 90% confidence. I believe it's just going to be the first column of the t table, so now go down to degrees of freedom of 24, and you should see right next to that 1.711. A moment here to talk about some of the questions that can come up on multiple choice in particular. It might ask you for the standard error. So if it asks you for the standard error, that's just this part, the 4.16 divided by the square root of 25. That's going to be a little bit more than 0.8. I'm not going to calculate it right now, but it's just this part. It might ask you for the margin of error. That's all of this. Now you take the 1.711 times the standard error to get the margin of error. Those are the most common, but I think there are at least a couple of questions in the test bank that ask for interval width. That's just the whole width of this interval. So 17.72 minus 14.87. Now, if you're doing this on a multiple choice question, you can save yourself a little bit of time on some of this. If the question asks for margin of error, you could just use your calculator to get the 14.87 and 17.72. If it asks for interval width, just get that whole width. If it asks for margin of error, it's half of the interval width. So just get that, this minus this, and then divide by 2 to get to the margin of error if you don't want to work through the whole formula on that. Now I think probably if it asks you for standard error, you're probably better off just calculating that part without using the stat function on your calculator. Okay, give me a second here to rearrange stuff in here so I can work through this. You can see the whole thing here. So this is a matched pairs t-test. The question will give you data, something like this, where you have pre- and post-test scores for some number of people, in this case just 5. That's because we're going to do the math on this and we don't want too large of a sample size for that. So anyway, when you get this problem and it's matched pairs, this is the same person here. Got a 16 on the pre-test, then scored an 18 on the post-test, 13 on the pre-test, 15 on the post-test, and so on. The first thing you want to do is write down those differences. So just 18 minus 16, 15 minus 13, and so on. So these are just the differences. Once you've done that, this problem is just a one sample t-test, one little other twist, but it's just a one sample t-test with these being your x values. So the pre and the post test scores are no longer part of the problem. We only used those to get our x's. We'll compute the sample mean. So if you forget how to do that, please review. And then, okay, somewhere over here. Here we go. We will compute the sample standard deviation. We'll do that by subtracting the mean, the 2, from each one of these values. So 2 minus 2 is 0, 2 minus 2 is 0, and so on down the column. Then squaring those deviations, just like we did on exam 1. So we have now add those up, the sum of the squared deviations. So hopefully you'll remember that the sample standard deviation is equal to the square root of the sum of the squared deviations. So this numerator is just the 6 right here, divided by n minus 1. That all comes out to be 1.22. So now in this problem, and you could do this with the one sample t-test or the one sample z-test as well, we're computing the mean and the standard deviation. On an exam, I'm a lot more likely to ask that in this problem than the other ones, just so we get everything together, because we're going to compute the x's anyway. So anyway, step one is get the differences, step 2 is compute the mean and the standard deviation of the differences. Now you can call these d sub I and SD and d bar and all of that, but really it's just these are you can call those differences or x's. Let x equal the difference, and if you do that, then there aren't any new formulas. You can just use the same formulas that we've been using. So we want to know if there's improvement, and that would be that the post-test greater than the pre-test, or the mean, that this is just the mean of the differences, is greater than 0. And all of the matched pairs or post-pre-tests or whatever that we do in here, post-pre-test is a repeated measure, which is a subset of the matched pairs. And I'm most likely going to ask, I'd say 90% plus of even of the multiple choice, and certainly a problem that I asked on an in-class exam will be, it'll either say post and pre-test or before and after. But upshot here is this is always going to be 0 in this class. You could make it other numbers, but we'll just look for simple, was there any improvement at all? And so I'm going to kind of go back and review a little bit. Once we get the differences, and here we go. Once we get the differences, then our hypothesis is compared to 0. Of course, we know we're going to need to calculate the statistics. It's just a one sample t-test now that we have. Just like before, we have the mean and the standard deviation. Our hypothesis, we just have to remember that is going to be compared to 0. Then it's just a t-test that like we had in the previous section. If I can find stuff now. Okay, we're going to find the p-value using our calculator. And there's 3 ways to do it. And I think I'm going to recommend that you do it just like we did in the last one, where you did stat, test, t-test. But now just make sure you enter 0 in for, I don't think I had that written down here, but I'm going to write this down while I'm doing this. Again, in previous videos I've gone through more than one way to do this, but I think I'm going to suggest you just, on your calculator, hit stat, tests, t-test, and then at the top, where it asks for input, select data. Actually, I left off a step here. We are going to do that, but let me go back for a second and say something else here, which I think is the easiest way. I could have done that and just entered in the sample mean and the sample standard deviation, but you're a little less likely to make mistakes if you do it this way. Go back to your post and pretest. Hit Stat and Edit. Enter these numbers in list 1. Enter these numbers in list 2. You can hit pause. I'm going to move on, but you may need to hit pause and do that. Then go to the top and highlight, have your cursor on L3, and then hit second 1. And what you'll see come down at the bottom of your calculator is L1 minus second 2. If you look on your calculator, second 1 is L1 and second 2 is L2. So we'll have second 1 minus second L2, and then it'll fill in these numbers for you. So list 3 will be the differences of 2, 2, 0, 3, and 3. So it'll populate that for you once you do that. So, alright, that's the, look at all that here. Now come back to this, sorry about that. Stat, test, t-test, input your data, and then for your null hypothesis, make sure you put 0. That is our null hypothesis. And then it's going to ask you where your data are at. You're going to put L3, and then go down and select greater than and calculate just like you would a t-test and obtain your p-value. It's going to be 0.0108, which is less than 0.05, so we'll reject HO. And so here's just a picture of that. We have our null hypothesis. We have the value of x bar, or if you want to do, if you did this with d bars, it'd be d bar 2. And again, this is the distribution of x bars, and the area here is the 0.0108, which we got from a calculator. And again, there are more than one way to do that. I just reviewed one here. There's some other earlier videos that have the other ways that you can do it. I think the one I put is the easiest on this one. But then, interpreting the p-value, if the mean, or the mean of the differences, is equal to 0, you could put that in Word and say, if there's no improvement, then there is a p-value chance of getting a sample mean, or sample mean of the differences greater than or equal to 2. Effect size, this just like we did with the other one. Sample mean minus hypothesized mean over standard deviation. It's 1.64. Using Cohen's criteria, that's a very large effect. Okay, here's a different kind of problem now. Move this stuff around a little bit. This one's different. We have a categorical variable. Now probably this problem would be something like in a simple random sample of 100, 34 students made at least an A or a B. Whatever it is, you could frame that in the form of a yes or no question. And we're putting them in categories now that they would say either yes or no, or made a B or better, or didn't. And we want to know if that proportion is greater than 0.3. Now sometimes it'll say percentage, but that's just out of 100 instead of 1. You'll need to convert that to proportions. We want to know if this is large enough. Now we have a categorical variable, so the rule's different. We need to know if both the number of yeses, which is 34, and the number of no's, which is 100 minus 34, those are both greater than 10. Therefore, we have a sample size that's large enough to guarantee a bell-shaped sampling distribution, and we can use then the z-table. Reject HO with the p-value is less than 0.05. That hasn't changed. The z-test is equal to the statistic, which is p hat. That's 0.34, or 34 out of 100, minus the hypothesized proportion, which was 0.3. 0.3 divided by the standard error, which will be the 0.3 times 1 minus that, or 0.7. Hypothesized proportion, yes. 1 minus that, or the hypothesized proportion, no, would be 0.7. That'll comes out to be 0.87. This again, z is just the number of standard deviations, or standard errors in this case, away from the mean. So we're 0.87 standard deviations above. You know that's not that unusual. It's not even one standard deviation above. But we got 0.3078 here. And so we'll take that 307, subtract it from 0.5 to get a p-value of 0.1922. So, if p is equal to 0.3, if the null hypothesis is true, then there is a p-value chance, 0.1922, of getting a statistic, in this case p hat, as or more extreme than what we had, the 0.34. So 0.34 or greater. Extreme is going in this direction because our hypothesis was p greater than 0.3 in our alternative. Confidence interval, the statistic, which is p hat, plus or minus the confidence coefficient, which is z, 0.34, and that 1.96 is probably pretty familiar by now, by the square root of p hat q hat over n. And make sure in the hypothesis testing we're using the hypothesized value, the 0.3 and the 0.7, but now this is from the sample, the 0.34 and the 0.66. So now we have our confidence interval. Remember too, if it's a multiple choice, you can get this using your calculator, and you would do that by stat tests arrow down to 1 prop, I think it'll say z, but it's interval. So you'll have to go down to the, I don't know, it's 8 or 9 or something like that, but the one that says 1 prop z interval. And then it'll prompt you to enter the x's, which would be 34, and the n, which is 100. And then you have to give it a level of confidence, which you would put 95, and go down and hit calculate, and it'll give you something close to 0.247. It'll say comma 0.433. So the central limit theorem, the shape of the population doesn't matter. If we take all possible sufficiently large samples that can be selected from the population, compute a sample statistic from each sample. So we could have the mean of the first sample, the mean of the second, the mean of the third, on and on and on, and compute a statistic for each sample. So we have population, we have individual samples, and then we're going to take these sample statistics, these means, the sampling distribution will be a bell curve with the mean of the, if you're doing this for the mean of the x bar is equal to the mean of the population, and the standard error equal to the standard deviation divided by the square root of n. I want to make one note here. The sampling distribution is a bell curve. These individual samples, if they're large enough that you can see things, will tend to look more like the population. So if the population looks like this, the sample, if it's big enough to see the shape, will also look like that. But when you take the means of those samples and distribute those, that will always be a bell curve. That's the sampling distribution. Be careful in the language, especially in multiple choice, that you understand the difference between population, sample, and sampling distribution. So large enough with means is that 15, 40, 100. If the population is normal, any n will do. If you have skew, you need at least 15. If you have outliers, you need at least 40. And if you have extreme values, at least 100. So it's this sampling distribution of the x bars that's a bell curve. Again, if we've drawn all the samples, computed a statistic from each, this is a distribution of x bars, the sampling distribution, and it has a mean equal to the mean of the population. As I said a moment ago, a standard deviation or standard error equal to the population standard deviation divided by the square root of n. For the sampling distribution of the p-hats, sufficiently large means both the number of yeses and the number of no's greater than 10, both of those. We have a distribution now of p-hats. The center of the distribution is just going to be p, or p hypothesis if you're doing a hypothesis test, but you could just put p there, with a standard error equal to the square root of p q over n. If you're doing hypothesis testing, it'll be ph qh over n. If you're doing a confidence interval, it'll be p hat q hat over n. But anyway, this is also a sampling distribution, and you could take multiple samples that were large enough and get a sampling distribution that's a bell curve, which would enable us to do a z-test or a z-interval for proportions. So the z-test and the t-test, all those p-values are only valid because we have the central limit theorem and we're going to have a sampling distribution in this shape. So if it asks you the connection between hypothesis testing and the central limit theorem, it's the p-values. They're only valid if we've met those conditions. And for the confidence interval, the connection to the central limit theorem is we're using these z and t values, and those are valid only if you have met those conditions for the sampling distribution. Okay, that's